In this section of sequences and series, we're going to talk about recurrence relationships. Now, a recurrence relationship is where we define each term in terms of previous terms in the sequence. So for example, if we have the sequence 1, 3, 7, 15, we have that the next term is found by doubling the previous term and then adding 1 to it. So if we wanted to find u5, we know that it would be twice u4 plus 1, which is 2 times 15 plus 1, which gives us 31. And then using this relationship, we could generate the entirety of the rest of the sequence, if we wanted to. It's also worth noting that a recurrence relationship is also known as a recurrence formula. These two different terms mean the same thing, but I mention it just in case it comes up and you're not familiar with it. So let's take a look at some examples. So here we have a couple of recurrence relations, and we want to find the first 4 terms in both of these sequences. The first one is fairly straightforward. Our recurrence relation is just add 4 to the previous term. We have that u1 is equal to 7, so u2, let's try a better u, is equal to 11, u3 is equal to 15, and u4 is equal to 19. And that's all the question has asked us to do. For part B, we have a more complex recurrence relation. And because it's defined in terms of 2 of the previous terms, we need to know 2 of the terms in order to generate the entire sequence. Whenever you're given a recurrence relation, you will be told enough information about the first few terms of the sequence to be able to generate the entire sequence. So, we already have the first 2 terms of the sequence. To get u3, we want to have 3u2 minus u1, which is of course 3 times 2 subtract 4, which gives us 6 minus 4 is equal to 2. u4 is equal to 3u3 minus u2, so that's 3 times 2 subtract 2, which is equal to 6 minus 2, which gives us 4. So there we have a couple of examples of just using a recurrence relation to generate a sequence. Our next example is more complex and is fairly typical of an exam question. So we have a recurrence relation, but we have a constant involved in it. We know what the first 2 terms of the sequence are, so it then asks us to find the 3rd and 4th terms, and then use these to find out what this value of the constant is. So if we look for u3, then according to our recurrence relation, we're going to get m times u2 plus u1. And of course that's going to be 5m plus 2. So we have part A finished. For part B, we're looking for u4, so we have m times u3 plus u2, so then we have m times 5m plus 2 plus 5. So this is where it starts to get a bit more complicated. Not a huge amount more, not actually that much more difficult. But now we get a quadratic expression for u4. So then in part C, they give us a value for u4. We now know that it is equal to 21, and we know that m is equal to, u4 is equal to this quadratic expression. So now we have m in terms of a constant, or at least an expression in terms of m is equal to a constant, so we can find a value for m. So if we subtract 21 from both sides, we get 5m squared plus 2m subtract 16 is equal to 0. So then we need to think of pairs of numbers that will multiply to make 16, but are also, once one of them gets multiplied by 5, we'll get a difference or sum of 2. So clearly we'll want 5m and m. And if we try 2 and 8, 2 times 8 will make 16. We need to have a different sign, and the 2 will need to be positive. So 2 times 5m will give us 10m, subtract 8m from that, we'll get our plus 2m. We have 2 times negative 8 will give us negative 16, and we have our 5m times m will give us 5m squared, and we're sorted. So then we have that m equals negative 2 or 8 over 5. We don't know anything about m, it can be any real constant, so we have two values for m. Those are our possible values. And we're done with this question. So, if you're happy with that, then have a go at exercise 6C.